When two objects meet head-on, their resulting motion stays locked to a single straight line. But physics gets more complicated the moment you introduce a glancing blow. When an impact is even slightly off-center, the objects deflect at diagonal angles. At this point, standard one-dimensional kinematic equations fail to describe the resulting motion because they cannot process movement occurring across multiple directions at once. You see this in a game of billiards, where players strike smooth spherical masses off-center to transfer momentum at specific diverging angles. It is visible when a child shoots a marble into a cluster of others, sending them scattering across the pavement on a two-dimensional surface. To predict the outcome of these multi-directional collisions, we must move beyond simple arithmetic and utilize the vector nature of momentum. Within this three-dimensional coordinate system, our incoming object is traveling exclusively along the horizontal x-axis toward a stationary target. Because the initial motion is restricted to a single axis, the momentum moving along the vertical z direction, up and down, is exactly zero. The law of conservation of momentum states that the total momentum of the system must remain constant. Since there was no vertical momentum before the impact, there can be no vertical momentum after it. This geometric constraint effectively locks the motion of both objects into a flat, two-dimensional xy plane, regardless of the angle of the impact. In this standard model, an incoming mass m1 moves with initial velocity vector v1 initial toward a stationary target m2 at the origin. Upon contact, they diverge into final velocity vectors v1 final and v2 final, defined by specific scattering angles θ1 and θ2 from the horizontal axis. These diagonal vectors cannot be calculated as single units in kinematic equations because they displace the objects along two axes simultaneously. To resolve this, we apply the principle of orthogonal independence. We mathematically decouple the single 2D impact into two independent 1D events occurring along the x and y axes. By projecting these diagonal paths onto the horizontal x-axis, we find the pure forward components of their motion, which are calculated using the cosine of their scattering angles. For this horizontal axis, total entering momentum equals the sum of horizontal components exiting. This gives our first equation, setting mass 1's initial momentum equal to the final horizontal momentum for both objects. The x-axis equation accounts for the preservation of the system's forward momentum, entirely independent of the vertical spread of the particles. We now shift our focus to the vertical y components, calculated using the sine of the scattering angles. One vector points up, while the other points down. Recall that before the impact, the system possessed exactly zero vertical momentum. To maintain this zero-sum state, mass 1's upward momentum must perfectly cancel mass 2's downward momentum. In the formal y-axis equation, 0 equals the upward momentum subtracted from the downward momentum, representing their opposing directions. Orthogonal resolution converts the diagonal interaction into two parallel algebraic equations, making the motion along each axis manageable. If we view these equations together, the variables we typically know are highlighted in white. The unknowns, the final velocities and the scattering angles, are highlighted in red. Comparing our resources reveals an algebraic gap: 4 unknown variables, but only 2 momentum equations. Even in a perfectly elastic collision, adding the kinetic energy equation provides only a third mathematical tool. We are still left with 4 unknowns. This is an underdetermined system, meaning the equations allow for an infinite number of possible outcomes. The math alone cannot predict the specific result of a two-dimensional collision from initial states alone. How do physicists resolve this uncertainty in a practical environment? They bridge the mathematical gap with empirical data. Solving the system requires physically measuring at least one of the final variables. A detector recording a specific scattering angle provides the missing variable. Once this value is known, the equations collapse into a solvable state. Vector conservation laws govern every impact, but determining the exact outcome of a 2D collision requires an alliance between mathematical resolution and physical observation.